everyone, thanks for coming. Today we're going to do a review of our week 8 lecture on ODE course. So in this week, we introduced the concepts about the Laplace transform. So before we talk about the Laplace transform, we first reviewed improper integrals. The type of improper integrals that we care about is the improper integral that the upper bound is infinity. So we define the improper integral to be the limit of this usual integral as capital A, the upper bound goes to infinity. If the limit for the right-hand side exists, then the integral converges, and we define the limit to be the improper integral if we replace A with infinity. If the right-hand side does not exist, then the improper integral diverges. So how to determine if the improper integral for a function from A to infinity exists? We use a comparison theorem. If we have a piecewise function f, if we have another function, non-negative function g, such that if the absolute value of f can be bounded by g, then if the improper integral for g converges, then the improper integral for f also converges. On the other hand, if f is greater than or equal to g and the improper integral for g diverges, the improper integral for f also diverges. Next, we talk about the Laplace transform. The Laplace transform is defined by taking the integral of e minus st times f of t. So here, the kernel function is e2 minus st. This is very useful for solving linear differential equations with constant coefficients. So, by applying the Laplace transform, usually we can convert some differential operator into multiplications. So if we have an initial value problem with initial condition defined for t equals to 0, we can apply the Laplace transform to convert into the s domain, and we solve for f of s, and then we invert the transform to recover f of t. If the growth of f can be bounded by some exponential growth, then the Laplace transform for f exists for s greater than a. This guarantees the existence of the Laplace transform. So if we apply the Laplace transform operator to the derivative of f prime, then we get s times the Laplace transform for f minus s0. Similarly, we can apply the Laplace transform to higher order derivatives to get the algebraic equations of the Laplace transform for f as well as the initial conditions. So this is very helpful for solving higher order differential equations. If we have the second order differential equation, we apply the Laplace transform. This is the Laplace transform for y, while capital F is the Laplace transform for the right-hand side. So that means if we invert this Laplace transform, we may be able to get the original f of t. So you can see that by applying the Laplace transform, we convert the differential equation into an algebraic equation. The inverse problem, which is to find the original function given its Laplace transform, could be more complicated. But if two functions are continuous as they have the same Laplace transform, then they should be identical to each other. So this is quite helpful because using the uniqueness theorem, we can guarantee that if we invert the Laplace transform, we get the solution to the ODE. The Laplace transform, this quantity could be complicated, but if it can be decomposed into the summation of many terms, and for each of those terms we can get their inverse transform, then the inverse transform for f should be the summation of the inverse transform for each one of those fi. This is very helpful for solving equations like the mechanical regulation and electric circuits, because we can always separate the Laplace transform for the right-hand side as a Laplace transform obtained from the initial conditions. Thanks for listening.